talk about things a little more generally, and then move away from a microscopic point of view. We're really focusing on like individual molecules in the last lecture. And so we want to think about kind of where can we take this information about interactions and kind of like blur over all of the intricacies of the interactions and just think about interactions as a general concept. Things attract, sometimes they repel. They have sizes. So we're going to take kind of a general, like more macroscopic approach to these things to correct them. And that will introduce the van der Waals equation, which you saw in homework 1. Will actually kind of justify the form of the van der Waals equation using our discussion today about interactions. So let me just go back to the interactions again. One of the important things is to understand chemically what causes interaction between atoms and molecules. And there are lots of different ways to interpret this. I have this particular way that I like to think about things where I break my interactions down into 4 major classes of interactions, all of which, as we'll see, as we've talked about, are all originating from the same kind of fundamental principle, which is that opposite charges attract and same charges will repel. And so they all kind of come, all of the interactions in chemistry are electromagnetic. In fact, that's what chemistry is. It's an electromagnetic theory of the universe at low energy. So chemistry starts to fail at the point where atoms start breaking apart. You have nuclei and protons, and really high energy, everything is just a soup of electrons and protons. That's not chemistry at that point. That's what you would call particle physics or high energy physics. But as you cool down that morass of electrons and protons and neutrons to what we would call low temperature, which was maybe thousands of Kelvin, we start to form molecules and atoms. So chemistry is the consequence of the electromagnetic interaction at low energy, at low temperature. And what we call low temperature in chemistry is very different than what I mean by low temperature in a physics sense. High temperature in a physics sense is tens and thousands and millions of degrees Kelvin, and low temperature is anything that isn't that. Think about the environment, the particle accelerator. So at the beginning of the universe, the Big Bang, really hot, really high energy. That's the same stuff that we have in chemistry. The big difference between chemistry and all of that is just temperature, just energy. So chemistry is at low energy. We really care about things at 300 Kelvin or lower. Things that are in the ground state have no energy. Those are molecules, condensed matter. That's where we sit. So all of this is tied into electromagnetism. Magnetism is chemistry. So again, Angie had a really good point last night. What about gravity? And I explained to you why gravity doesn't matter. And we had this conversation last class. And we're jumping ahead a little bit with this. But I think it's important to consider the different forces in the universe and how chemistry plays that role. And I really like this discussion here of the 4 different types of forces in the universe. Right? There's 4 forces. There's gravitation, electromagnetic. You know what these do. You understand these. You may have never heard of strong or weak. The strong force is what keeps nuclei together. It's the force, the attractive force between protons. Actually, the things that make up protons. It's the things that keep protons together. Protons are not our fundamental particles. They're actually composite particles of smaller particles called quarks. And quarks are kept together with the strong force. It's the glue that keeps the proton together. That's the strong force. The mediator is the gluon. And then there's the weak force, which is generally only in chemistry related to beta decay and certain types of radioactive decays. Right? It's a very weak force that very rarely happens, hence the name. It's really not a big deal in chemistry, except for nuclear physics, nuclear chemistry.
Like how they call the sticky quark, the gluon.
Yeah, well, and that's exactly so. Gluons are really so. Here's their. I don't want to spend too much time on this because you'll get me talking the entire class about this. But what I want to look at are the relative strengths, right? We can compare each one. And so the strong force is interesting. It gets stronger the further things are apart. So electromagnetism, as you know, goes 1 over R3 or 1 over R squared, depending on what you do. The force goes into 1 over R squared. If you double the distance, the force becomes half as much. The strong force increases by a factor of 2 when you go from close to distant. That's the opposite. So physicists usually define a strong force to be a strength of 1. Electromagnetism is defined to be exactly, it turns out, 1 over 137. Right? So it's about 100 times weaker, a little more 100 times weaker. The weak force is about 1,000,000 times weaker, and gravity is 10 to the 39 times weaker. Right? This is why gravity doesn't happen. All of chemistry happens at this scale. So in order to understand, let's imagine you have some measurement of the interaction between a positive and negative ion, and the strength is mediated at this strength of 1 over 137, and you want to measure the gravitational effects on these. In order to do that, if you have, say, 2 significant digits at this level, in order to measure gravity, you would need another 38 significant digits. Okay, there's literally nothing in the universe that precise. The most precise measurement in history of physics is about 13 or 14 significant digits. So we're still off by an order of 20 digits or so before we can even think about gravity. So gravity is completely irrelevant. Yes, and the reason why they're called gluons, I mentioned this because they literally are like glue. I mean, of course, glue gets weaker as you stretch it, but the strong force, the thing that keeps together, the gluons that keep things together, they get the gluing force becomes stronger the harder you pull on them, which is very strange. And in fact, what happens if you take 2 quarks, they're always paired together. Quarks never are separate. They're always in pairs. And if you were to take a pair and split it apart, it would make 2 new pairs. That's kind of a crazy concept. It turns out the energy and all the calculations work. Pull 2 quarks together, you make 2 pairs of quarks. 2 new quarks get created. So they always come in pairs. So that's very crazy physics, very, very different than what you see in electromagnetism. Again, we don't have to worry about it. It's only important at distances scales on the order of 10 to the minus 15 meters. That's about 1,000,000 times smaller than the average scale in chemistry. Okay, so these only matter at the nuclear scale, or size of the nucleus. So that we only really care about that at high energy. So we don't worry about it. So everything is electromagnetism. Right? So I could just say that, right? I could just say that molecules interact through electromagnetic theory. That's great. So it's true, but we should be a little more subtle about it. Because there's different types of electromagnetic interactions, as we saw. So the 4 that really matter is electrostatics, right? Dipoles and dipoles, ions, plus and minus charges. Induction, right? That's the concept of taking one molecule that's polar and bringing in another molecule and inducing a dipole moment in that molecule by biasing its electric field, the presence of another dipole. That's a weaker effect, but it generally generates most of the weak interactions that we see in chemistry. And the last 2, of course, are the van der Waals force, the dispersion force. We talked about how that's due to random correlations in electrons between 2 objects. It's a much weaker force, but it's universal. Everything has it. And then there's the exchange force, which is an interaction between 2 electrons swapping each other's positions. Exchanges of electrons. And this is a interaction between a negative particle and a negative particle. And those repel. So anytime you exchange 2 electrons, you gain some energy. It costs money, it costs energy to do. And a system, in order to equilibrate, has to satisfy all the possible combinations that are available. So there's always a cost. Any interaction always brings this additional repulsive cost, because when you bring in 2 balls of electrons together, there may be positive regions that attract negative regions, but in general, you're still bringing electrons close to electrons, which allow them to exchange, which raises the energy. For repulsive. And the best way to think about it is, again, dispersion is an interaction between regions of negative charge and positive charge, electrons moving in anti-correlated ways to open holes and close holes. And exchange is the opposite, where electrons have to interact with themselves in order to exchange. And that's a repulsive effect, because it's between negative and negative instead of negative and positive. And so the examples I gave you, and I'll give you a couple more today, This is where we stop. We looked at the classic hydrogen bond between two water molecules. This is what we call the canonical hydrogen bond. It's what we compare all hydrogen bonds to. It's the hydrogen bond between two water molecules. And we showed that largely, not surprisingly, it's a very polar molecule. We know that water is fairly conductive compared to, say, organic solvent. So it's very strong electromagnetic, electrostatic, and some induction forces. Water is not super polarizable, which is why its induction is smaller than its electrostatic by a factor of 4. You can kind of see that borne out in the energy. There's a little bit of dispersion. Yeah, not a lot. And that has to do with the orientation of the two molecules. In a hydrogen bond, you have this very directional contact. It's like two fingers touching in a Chinese finger trap. There's not a lot of surface area in that contact. It's a very directional electrostatic interaction. And dispersion forces, remember, the things that make that strong are having a large surface area. The two plates have to be big in order to feel a big force. So it's about surface area and contact. So there's not a lot of dispersive energy stabilization in water because they don't have a lot of surface area of contact. And then again, because electrons and charges are moving back and forth, right? There's this biasing of electrons through induction that kicks on the exchange. Anytime you get an interaction that's stabilizing, that also increases the probability for exchange. They come hand in hand. So as these numbers get more negative and more stabilizing, this one gets larger as well. Okay. But in the end, the attractions, the net attractions win out. Even though, so therefore you don't, it's not as stable as you would expect because there's always this repulsion force in there, but you need it to understand the full structure of this full interaction. And when you add all of them together, you get very good agreement with experiment. And the next case, the last case we looked at was this CH pi interaction. This is something that's somewhere in between the two boring plates and a water dimer. We have this like hydrogen bond like connection, but the hydrogen now isn't really being bonded to something that's electronegative like an oxygen atom, but rather the negative charge density of the benzene ring. A bunch of pi electrons, a little bunch of double bond electrons orbiting this ring in a current, and that's what the H is interacting with. Those are much more rigid electrons, not very electronegative. They're there. And therefore, the electrostatic effect and inductive effects are much smaller. But we have much more contact. We have these two rings that are in contact with each other. There's a lot more surface area of interaction between these two molecules because they're large and kind of fat. And so the dispersion interaction compared to water is much larger by a factor of almost 3. Because we have this contact, but once again, when you have dispersive contact, you have a large surface area of interaction. You also have a large probability of exchange. And so all that dispersive energy that we stabilize the system by, we basically kill it all with exchange. It all cancels out. So all we're left with is kind of a few nickels and dimes of interactions that are left over. But still, again, it's enough that the net result is an attraction that's very close to experience. So let's kind of go down the list a little further, right? We've gone from electrostatic to something that's a little less electrostatic and a little bit of dispersion. So what happens when we turn off the electrostatics and just go to dispersion? What about a system that is completely dispersive? I'm going to show you 2 more examples today. One is pure dispersion, and then I want to show you a cool molecule from my thesis a dimer that I just happen to like. So the next example we're going to look at today is one that we considered when we talked about the way that the gases, when we talked about those curves of the gas pressure and volume versus temperature or pressure. And we saw that some of the gases deviate. One of the gases that deviated the most was methane. So let's look at methane dimer. Right? How does methane interact with itself? Now, when we think about the different criteria that cause intermolecular interactions, what do we want? We want a lot of surface area. We want negative and positive charges, dipoles. All these things are great. The problem with methane is, first of all, it's a very compact molecule. It's a tetrahedron. It's just got hydrogens and one carbon. It's very small. It's effectively a sphere. And so we're interacting two spheres. And methane does not have a dipole because it's a tetrahedron. Tetrahedrons don't have dipoles. So it's a dipoleless molecule that doesn't have a lot of flat surface area of contact like a plate. So the electrostatic interaction is going to be really weak, but also maybe the dispersion interaction is going to be weak too. There's not a lot of contact area. So the way methane dimer looks, and actually, strangely enough, this was a point of controversy in the 1990s. What does dimers of methane look like? There's lots of different ways to orient two methanes together. And it was never very clear which one is more stable. It wasn't until the late 90s that we figured out that, in fact, what happens is perhaps the most boring combination, where basically the other methane is just upside down. Okay, like this. All right, so I've got one methane that looks like this, and the other one's like this. All right. For a long time, people thought that one of the hydrogens on methane creates a hydrogen bond with the carbon. So a CHC hydrogen bond. That's a very, very weak hydrogen bond, but we're also dealing with weak interactions. So anything is possible when it's weak. And it turns out that that's not the most stable form. It took us a while to figure that out, but we're confident the most stable form of methane is this upside down flipped isomer. And let's look at the energies for this. And electrostatic, induction, dispersion, and exchange. We're going to look at the total, and we're going to compare it to experiment. This is before. Well, once again, this has no dipole. These are very poorly polarizable molecules. So the electrostatic interaction is basically negligible. The induction is even more negligible. Remember, we discussed that in general, induction is a smaller effect than electrostatics. So naturally, it's smaller by a factor of 6. Basically not. It's basically 0. My error is actually higher than this value. But we'll just write it down for now. Okay. The error is a more for calculations, it's hard to define an error because you don't know if it's a correct theory or not. So basically, they're 0. And of course, there's some dispersion. It's the strongest force, right? Because again, that's all that's left. There's still some surface contact. Everything attracts everything. And so here's that leftover attraction that you get between everything. Okay? But once again, we have a system that basically takes in these two balls of electrons with no dipole. And so they basically just look like balls of negative charge to each other. They've got no positive, no negative end, just negative everywhere. So when you bring these two together, they're attracted dispersively. Very poorly attracted induction and electrostatic because there's no positives in there. There's two negative balls. So you bring them in, they stabilize, but also exchange kicks in hard too. Is you're bringing effectively two negative balls in, so any dispersive effect is going to be compensated by exchange. Because it's not exchange between positive regions and negative electrons, it's exchange or interaction between negative and negative. So the exchange is very high. And in fact, it completely dominates the electrostatic interaction. Plus 0.69, right? So dispersion is basically negated completely by exchange. But once again, when we add the numbers, we end up having more negative than we have positive, right? There's slightly more attraction when we count our nickels than there is repulsion. So this is still net attractive, but just very weakly attractive. So it barely binds at 0.1 kcals per mole. And the experiment, sorry, that's the wrong screen. I have the experimental number right here. Doesn't agree exactly. It actually experimentally, it's more stable. So that's very interesting, right? All of the other strongly bound interactions we just looked at, strong compared to this, agree very, very strongly. Right? They're only off by a small amount. But here the error, right? The percent error here is like 300%. Off by a factor of 3. And in the wrong direction, no less. It doesn't overbind it, it underbinds. Right? So what the hell could that be, right? I thought we've accounted for all of the forces accurate. Right? So how can it be that there's some additional attraction? Well, the fact of the matter is that this is just an approximation. This combination, this partitioning scheme that I've chosen for the interactions is just an approximation. So it turns out that there's an additional level of terms that appear at the next level, where, for instance, imagine if you have some exchange of electrons across the methane molecules, and that exchange causes an induction in a dipole, right? Maybe you've jammed some more, maybe you put some electrons here into here, and now you have more negative charge, now you have more positive charge here, right? There's a difference in positivity. And so now you've induced a dipole moment between the two molecules. And so you would have an exchange, I don't know how to say this, an exchange induction energy as well, where you have an induction of a dipole from the exchange event or from the dispersion event, right? There would be, or there would be some electrostatic interaction, right? So you can have responses to responses, if you will. And when you accumulate those extra approximations, think about the induction due to exchange or the induction due to dispersion, and you start to add those additional terms, then the total energy starts to match experiment. Okay, so one of the conclusions we can make here is that this partitioning scheme, just like anything, is just an approximation. But there's an additional layer of interaction terms. So, for example, exchange generated induction, for example, that become dominant. They're very, very small, right? Those terms might only be 0.005. They might be on this order, right? But there's a lot more of them. Imagine that the next level of approximation is you take combinations of all of these. So what's the induction you get from the electrostatic response? What's the induction you get from dispersion? What's the exchange you get from induction? Right, so you have all these different combinations. We have four of them, so there would be 12 combinations. There'll be an additional 12 terms at the next approximation, and those are going to accumulate that extra 0.4 kcal. Right, they're all very, very small terms. They're all probably in the order of 0.01, 0.02, but there's 12 of them. And so then you get that additional stabilization by some amount, and that's going to get us closer to the correct answer. So there's this Jacob's ladder of approximations that we do at PCAM, right? We just have to make a choice that's appropriate for our problem that allows us to explain the problem in as simple of a way as possible, but also completely. Right? Occam's razor always says that the best explanation is one that explains all of the behavior with the minimum number of parameters. So this is a good minimal set of parameters that allow us to qualitatively, even quantitatively explain interactions, but you can see there's a limit. there's another layer of interactions buried in there that become dominant when these interactions become small. So it's always about competition and where you want to choose your approximation to best represent your system. So if we're dealing with methanes or we're dealing with helium atoms, things that are not polarizable, don't have dipoles, we have to think about higher order interactions because those small terms are on the same order as these big ones. Whereas with hydrogen bonds, we don't have to care about that at all. Hydrogen bonds are electrostatic. We don't really care about the underlying effects because they're very, very small compared to these terms right here. Right? So much of chemistry and physical chemistry as a whole, when we want to model things, is we build this Jacob's ladder, this kind of structure, a framework of approximations that allows us to pick and choose how deep the rabbit hole we want to go. And the deeper we go, the idea is that it's consistent, and that the deeper you go, the more accurate you get, right? Because we could keep making theory as complicated as possible, but it doesn't predict anything. Who cares, right? We need something that approaches the correct answer. And everything in chemistry, when you're modeling it, has this approach. You start with a very base level framework. In Gen Chem, that's Vesper theory and Lewis dot structures, basic enthalpies. And then we go to another level and then another level, right? And then eventually you're starting to think about these things. And then you're like, okay, this isn't good enough. I need to go even deeper. Right? Well, theoretical chemistry as a whole is this path. It's understanding how to efficiently and accurately measure the weakest interactions. Because if we can understand those, we can understand the big ones and therefore understand the big picture. Let me show you one more example. This one I'm not going to draw because you'll understand why in a second why I don't want to draw it. So this is a paper that came out of a molecule or structure, a complex, a cluster, a dimer, if you will, of a molecule that I studied in my grad school. It was actually one of my first papers. And it's just a beautiful structure. And I want to talk a little bit about it because one of the things that maybe we're starting to see is that there's a competition of effects. Some things are electrostatic, some things are dispersion. This example I want to show you is a really good situation where there's actual competition between the two effects. What does it look like when the dispersion force is just or as strong, almost as strong as the electrostatic force? Not when they're one stronger than the other, but when they're comparable. So let me show you this. Find that it's dug deep in my 300-page dissertation. Okay, so I'll go ahead and start writing while I dig up the picture. Right, we're going to look at phenol dimer. If you don't know what phenol is, it's really easy to draw. The benzene, that's not a benzene. With an OH group. You see why this might be an interesting dimer? We can form hydrogen bonds with the OHs. But we also have a benzene ring. The benzene rings love dispersion. So we have a really natural competition between the two. And here I'll show you a picture of the experimental structure of this molecule. So this is what the structure looks like of the cluster. I'll find a better picture of it. This is side on. So this is one of the benzene rings. Right? This is one of the phenol monomers. I'm looking at it side on. Here's the oxygen. And here is the other benzene ring coming in with the OH bond, hydrogen bonded to the other oxygen. Okay, so what do we have here? Well, we have a hydrogen bond. And then you go in and you actually calculate that the angle between these is about 60 degrees. And that is set by dispersion. Now, how do I know that? How do I know that this 60-degree angle is set by dispersion? Well, so here's a really clever thing that I realized that I could do. Actually, I didn't realize it. So let me tell you the story about this. There were a couple of papers in the literature before I published this. I published this in 2012. There were a couple of papers in the literature. People had studied this dimer and a couple of different types of spectroscopy and computation in the late 90s, early 2000s. And one of the discussions they were having was this angle. How wide is this angle? All of the spectra that people take of phenol, it's very clear that there's a hydrogen bond between the OHs. That's great. But when you go do calculations of the structure in the 1990s and you ask what's the hinge angle from predictions, the values are all over the place. And it wasn't really quite clear why that was until the 2000s, the late 2000s, early 2010s, where this concept of dispersion, which we knew about for a long time, of course, and I told you stories about the 1800s, van der Waals was around the early 1800s, about how to properly model dispersion. It's a very hard thing to model properly. And people realized that the modeling that we were doing for molecules treated dispersion very poorly. So let me show you a picture of one of the structures that one of the old papers published compared to my experimental structure. Okay, so just as a quick explanation, these little blue spheres here, these are the experimental positions of the atoms. Okay, this is what I calculate from my data. So this larger gray thing with the black lines, that's a calculation. So I'm just comparing my experimental structure to a calculated structure. You can see they agree very well. So let me show you the structure from the 1990s compared to my experiments. So this doesn't, so this method, this B3-lip method, by the way, this concept of B3-lip not dealing with dispersion is central to Homework 2. I actually this is actually central to that analysis, to this discussion. Not to that analysis, it's just the context. But dispersion is treated very poorly here. And what do you see? Well, the ring is far away. Right, this hinge angle is like 120 degrees or something like that. Right, not only is that the ring 120 degrees away, but it's tilted in some sense out of plane. Okay, this ring these are lined up in roughly the same orientation. You know, the A, B, and C axes are roughly the same. They're rotating a little bit. Right, but not only is the ring moved away, but it's also rotated away from the other ring. Right, this ring's starting to face out now. Right, so this is what dispersion does. Right, you have this connectivity that's electrostatic, and then what the dispersion does is optimize that angle to bring in that ring as close as possible without the exchange dominating. All right, so this is a system where electrostatics and dispersion compete directly. Right? This is if you only treat the electrostatics correct. This is what you get when you treat both of them. Right? Very, very big difference. And we can just look at the numbers for this. And I'll prove to you. So these numbers I calculated after. So the method that I used to calculate these numbers was not invented until after I published this paper. So this paper came out in like 2016 for this calculation. So this is fairly cutting edge stuff.
So did you invent it?
No, God, no.
How did you use it?
I'm pretty good at computational chemistry. I'll just put it that way. The things that do these calculations are just packages you can download on the internet, install on your computer. In fact, all of the calculations I did here, I use free software that I just found on the internet. You just have to have the know-how and the experience with computers to deal with this stuff. These programs don't have like graphical user interface. They all run on Linux. So it's a little complicated from a computer point of view, but the software is really well documented. It's free. There's lots of tutorials out there to learn this kind of stuff. So let's look at these numbers, right? Electrostatic and induction are large, but again, they're distributed differently. Remember, electrostatic is always going to be stronger than induction when you have dipoles. Dipoles interact more strongly with dipoles than induced dipoles by about a factor of 3 in this case. There's some amount of dispersion energy. right? And that 4.89, all of that energy comes from this interaction. I don't have a calculation for this structure, but the dispersion energy is much smaller. I don't remember what it is. The exchange energy, again, is very large because there's a lot of electrons moving back and forth. The total interaction is 7.37. And I have an experimental number for you, right? Minus 6.65. So as you can see, it's not quite perfect. But here's the other limit, right? So this is, in some sense, a far more complicated system than anything we've looked at before. Right? Everything we've looked at before, really, really simple molecules. Right? Water, benzene, that. Here we've got a much more complicated system. We've got benzene, we've got OHs, there's all sorts of different effects. They're a big system, so your error generally jumps quite a bit. And we generally find that in calculations, as long as you're within about a kcal, that's a good calculation. And we're within about a kcal. So this is what I would call an agreeable calculation that agrees. And it's not, I can't do much better here without going to a much higher level of clear, much more deep calculation. But it gets you the right idea, right? That this is a system that where dispersion and electrostatics compete quite a bit. Here's the really cool thing. What happens when you add another phenol molecule into this? I'm going to show you two more pictures. No more numbers. Right? But one of the cool things about these intermolecular interactions is that they're very standard and like they're progressive. So as you start to build things, you can kind of predict how the structure is going to form and how it's going to morph as you make them more complicated. If you understand, like, if dispersion is going to be dominant here, or the hydrogen bonding is going to be dominant, there's going to be competition. In some sense, that really limits the amount of possibilities you can have to arrange things together. And so when you go to the so what also I looked at in my paper was the trimer of benzene or phenol. And that's a beautiful picture, beautiful structure. And I'll compare it now to the dimer. So this is the trimer and the dimer. So one thing, this is the hydrogen bonding length. You may notice, well, first of all, one thing that you may notice is that the rings come in quite a bit more in the trimer. And again, that's because there's three of them. The dispersion effects is now 33% larger than it was before. And so the rings really want to bring in together. It makes this beautiful barrel structure. In fact, it's threefold symmetric. Each one of these benzenes or phenols are exactly the same. So if I took this one and put it over here, it would be the same thing. It's a beautifully symmetric molecule. But the thing that one of the things that's really interesting about this system is that what I've done is I've taken a hydrogen bond and I've extended it to a network of free hydrogen. Each one of these hydrogen bonds are equivalent. So it's threefold symmetric. They're all the same. But what has happened? The hydrogen bond has shortened by 0.1 angstroms. Now you may say that's completely, who cares? Right? It's a small amount. But in reality, that shouldn't happen. Because when you add, the idea is that you've been talking about interactions between two molecules. So if you bring in a third molecule, there's going to be interaction between these two, these two, these two, right? Basically all the pairs. Right? And each pair effectively feels exactly what it feels in the dimer. So you would expect that this bond length for the hydrogen bond should be almost exactly the same as this one. Right? It's just like we've added another one into the system, but it's shortened. And it turns out the reason why it's shortened is because one of these hydrogen bonds, one of the three, is stronger than this one. The addition of the network by making this one hydrogen bond align into a triangle has actually strengthened the average hydrogen bond. So what this means is that the strength of a set of interactions is stronger than the sum of the pairs of interactions. Right, if you think about the interaction between these two, I don't know why it killed me. That's weird. I didn't touch anything. If you think about this having some strength of 1, then when we combine 3, we have how many pairs? 1, 2, 3. You would say, okay, well, the strength of this is now 3. Then you go calculate the number and you find that the strength isn't 3, it's 3.5 to 4. But the presence of an additional molecule has strengthened the other bonds. So what's happened is that when things combine together, they don't combine like pairs, but they find ways to stabilize that takes advantage of the fact that there's more than 2. Right? So these bonds are we call them cooperative interactions, meaning that the strength of the combination is greater than the sum of each interaction. The interactions self-support themselves through something called cooperativity. And hydrogen bonds in particular are like that. Hydrogen bonds are famous for that. We call these cooperative interactions. And just as an example, in liquid water, the percent strength due to cooperation is about plus 15%. So having water interact with itself with another one, right, to create these networks, provides an additional amount of stabilization, more than you would get if you just added the pairs together. And it's about 15% water. That's a lot of energy. So what that means is that if you have a water dimer and it takes so much amount of energy to break it, when you go to a trimer, it takes more than 3 times that energy to break all 3 bonds, because there's an additional stabilization that arises from the fact that there are 3 new. So this is a very, very simple idea of what's called a mini body effects, which are things that appear, interactions that appear only in the presence of many objects. There are these collective things that appear that would not appear otherwise in pairs. Water works together as a team to strengthen itself. That's one of the reasons why water is so sticky and so hard to boil and doesn't like to have much vapor at room temperature compared to other things like it, like H2S. Hydrogen sulfide is gas at room temperature. Because the hydrogen bonds that it forms are not only very strong, but the more of them you have, the stronger they get. It gives you an extra 10, 15, 20, sometimes even 30%, depending on the structure and the conditions, additional stabilization. And so the water is really, really tightly bound. It really does not want to break apart. And that really drives hydrophilicity, right? Things that are hydrophilic really, really take advantage of this extra cooperativity, right? You get an advantage by binding to more waters than just one. Right? So it's not just water or not, it's water plus additional, you get additional kind of extra stuff on top, right? When you buy a meal plan, you get 21 free swipes. When you bond with water, you get 15% more energy for free. It comes for free. So there are whole groups and whole studies that really study these cooperative effects, and they're very important in modeling biochemical processes and other things, and especially in aqueous solution. Now, I just have one more picture to show you. So what I've done here, right, we've just considered the option of adding another molecule to phenol. And we see that we form these barrel-like structures. And they have what looks like a water trimer in it. What happens if I add another ring? Ah, good. I have an answer for you. So that's another paper I studied in about 2018. And I wanted to ask the question now, what if I take phenol and I replace the benzene with a naphthalene instead? Do I also see the same effects? And I'm not going to post this on the paper, but instead I'm just going to show you the results. I'll just pull up the paper. Oh, great. All right, hold on a second. So I published this in Journal of Physical Chemistry like about 6 years ago. And so one of the things that we thought was, well, what I originally thought was going to happen was that way we get something that looks like this, but you have another ring. Basically, they would kind of come in together, but the two oxygens would still be bonded together. It's kind of like you get a little more stacking. But what you end up finding out, and first of all, this was something that was studied in the IR and they got the answer wrong. So I corrected the answer. But it's a very difficult problem. It's very, very subtle. What you find instead, let me find it here. I forget which one I actually picked here. So this is the structure that I thought originally. This is what we call the Henn structure. This is the phenol dimer equivalent. This hydrogen bond here, and then you've got the two rings that are kind of sitting out. This does not form. It's completely unstable. Instead, what actually is preferred is that now that you have an additional benzene ring, dispersion becomes stronger. Dispersion dominates. And so the rings stack on top of each other instead. The problem that we had, so these are all named after Seiki. Seiki is the guy who did the IR. And he couldn't figure out where the oxygens are with respect to each other. So he gave in his paper 5 different possible structures that agree. A, B, C, D, E. Notice that in most of them, there's 2 that the oxygen are off the side, but there's one where they're hydrogen bonded here. And he says that these are the correct ones. That what happens is exactly like what we expect in phenol, is that you add another ring, and what happens is the rings stack on top of each other to maximize the dispersion, but you still get some free hydrogen bond. It's completely wrong about it. The correct answer is this one, where the hydrogens are the oxygens are on opposite sides of each other. They don't talk to each other at all. And when you look at the interactions of these systems, this is a very complicated picture, but the idea is that the oxygen, you can't see the other one, it's on the opposite side of the molecule. There's no hydrogen bonds in it. This system is completely stabilized by this. This is an interaction surface. It's just a flat plane, right? It just looks like 2 plates put together. It's all dispersion. And so when you go from phenol to naphthol, you've generated enough dispersive energy that the hydrogen bond doesn't matter. Turns it off. We were able to confirm that that was the case. So it's very, very cool, right? So it's a very, very subtle effect. And there's always a fine balance between these. And it really comes down to the structure. Okay. Any questions about that? It's a good little bit of real chemistry.
I think you had a graphic on the page, but if you just keep adding them, they just keep stacking up.
Yes.
Okay.
Yeah.
Yeah, that's what I think that green one is.
Yes.
Right?
In fact, let's look at DNA, for instance. DNA stabilizes with both forces. Again, forgive me for Googling everything, but this is a terrible picture. But DNA is stabilized through the double helix is stabilized through 2 processes. The individual helices are locked into place by pi stacking between adjacent nucleobases on the same side. Right? Nucleobases are heterocyclic aromatic molecules with tons of dispersion. So they're locked into place here, and then on the other ends, right, they connect to the other side of the helix through hydrogen bond, AT and CG. Adenine, thymine, cytosine winding.
You know, I've heard that like in biology and whatever, but I've never actually thought about, yeah, that happening.
Yeah,
So
so this
nice
is,
to
so,
see it.
so this is, these two forces are the source of the general thermal stability and actually photostability. One of the really cool things about this dispersion interaction between the two rings is it actually helps to stabilize systems when they under DNA under a lot of stress. So as you may know, one of the things that is brutal to DNA survivability is ultraviolet radiation. Right? These heterocyclic rings are very, very strong absorbers of UV radiation, and UV will just ionize them and blow them apart. Right? So UV, that's one of the things that causes skin cancer is DNA degradation and mutation by radiation. And so one of the things that these dispersion interactions provide, these strong dispersion interactions provide, is an energy sink for that radiation. Imagine that a UV photon comes in and excites, ionizes, or blows apart. Let's say excites one of the nucleobases up in the ring somewhere. And what happens is that energy gets transferred through the pi bond, the interactions, the dispersion interactions, each of the nucleobases are in some sense talking to each other. They're coupled through their dispersive connectivity. And so any sort of information that's encoded in the electrons from that perturbation from the UV radiation, there's some probability that through exchange or dispersion that information or that energy is transferred to the next one, and then to the next one. And eventually we start to fractionate that energy out. Right? So the dispersion interactions actually stabilize DNA. They help distribute the forces that it feels from outside perturbations and destructive actions. Okay, that was my one biochemistry discussion of the day. So very, very deep, rich, interesting. You could spend your entire life thinking about intermolecular interactions. I've spent 15 years doing it, so I trust me, you can do that. So what I want to do for the next 10 minutes or so is to, now that we understand these interactions, how does temperature come? All of these interactions are true at 0 Kelvin. They just exist. But we haven't included heat yet, because heat's going to mix everything up. So how does heat contribute to interactions? And we have a hint. 10 pages ago in our notes, about a week ago, let me go back to the slide. We looked at these different deviations. And we looked at the deviation of the compressibility factor Z, PV over RT, for methane, as a function of pressure and as a function of temperature. And the temperature one is the important part, right? We're adjusting the amount of heat in the system. And what we see is that as we lower the amount of heat, the deviations negative and positive become dominant. They start to take over. And as we start to cool or start to heat up, those interactions seem to contribute less and less to the system. And you can imagine that if we go to thousands of Kelvin, it's basically a flat line and acts like an ideal gas. Okay, this is 100% true. An ideal gas is only ideal at infinite temperature or 0 pressure, going to 0. It's diminishingly small pressure. So I know that that's the case. Right? But what I've just explained to you are forces that exist no matter what. All of these interactions, they have no temperature contribution. They just exist. If you have two molecules in some space at any energy, they feel these forces. So why does it feel like the forces are getting washed out as we raise the heat? So we're going to have to think about how these two sources of energy are balanced in the system. So we're going to have to think about things a little more carefully. Right, so we're thinking about non-ideality of a gas or a molecule or some liquid or something like that. How does heat contribute? The way I want to think about this is, again, remember, heat is just energy. So what I want to think about are how does the energy of the interaction change as a function of temperature? What's happening is that the heat's becoming greater and greater and the interaction seems like it's turning off. Well, what we're gonna see is the interaction doesn't turn off. It's just that the heat kind of soaks them. The heat basically just is overlaying the interactions, and the interactions are negligible compared to. Well, I want to show you what that looks like somewhat intuitively. How does heat contribute to an interaction? So this allows me to introduce a new model, really simple model, that allows us to just kind of think of an interaction as a function, just to do a little bit of algebra. So something we can plot. I want to do something that we can plot. So we'll look at a general model. For dispersive interactions. Right. So I'm not going to worry too much right now about dipoles and things like that. I want to go back to the picture of just having some balls of charge and mass. And just very, very general. The model we're going to look at is a model called the Lennard-Jones potential. And I just need to set up a little bit of geometry so we understand the potential, the model. The idea is this. We have two balls, two spheres, A and B. And they have some distance between each other that we'll measure at the centers. Let me give you a different color. See that? We have these some distance we can measure from the center of these balls. And we're going to define some width, some radius to these spheres. And just some radius. I should maybe I should call this D instead. So I can call the radius R. Right? And then we can say that each ball has some radius R. Right? And what we're going to say.
Are they equal size?
It doesn't matter. They could be different. Let's assume they're the same size. That might make it easy. We're going to assume maybe I should say they're both A. Okay. They can be both. We can have mixed ones. That's a little more complicated. It doesn't matter. And what I'm going to say is that this interaction has a potential energy. And it has there are two options. So the potential is a function of the distance. And the potential has a limit when we're really close together, and a limit or a form that when they're far apart. So there's two different answers, two different potentials. It goes as 1 over r to the 6th, or sorry, d to the 6th. If d is greater than r, okay, so if the molecules, if the balls are far enough that they're not touching, it goes as 1 over 6th. And then 1 over d to the 12th if d is less than r. Okay, so all this is dispersion and exchange. The idea is that we're going to treat the molecules and the atoms as like slightly plushy spheres. You can kind of push them together, but they don't want to be. So together they feel a nice force, 1 over 6 at distance, that's attractive. And then there's this really, really, really hard force that kicks in when they're too close. That pushes them apart. So exchange and so this is dispersion. And this is exchange. Okay. There's different terms for this, but this is what's called the Lennard-Jones. And so the total potential, we often write like this. Use a function of D is equal to a number called it's equal to 4 epsilon let me call that a different color so we have it notated. This is a constant. This is a molecule specific constant. Times another constant, sigma, over d to the 12th minus sigma over d to the 6th, right? And these are molecule specific. We'll learn what these each mean in a second, right? So each molecule or each atom has a different epsilon and sigma. All right, we can already start to think a little bit about what these mean. The units of this are energy. The whole units of all this over here has to be energy. We look at sigma here. Sigma is being divided by d. All right, so let's say sigma has the same units as d. Distance. Okay, so sigma is some distance. And so this is unitless, because you have distance over distance, distance over distance. This is unitless. And the overall units of this is energy. So epsilon would have to be energy. Okay. So what we're going to find is that sigma has something to do with the length scale, the average distance, and epsilon is the strength of the attraction. And we'll see that when I plot it. This is the attraction strength. And this is the average length, the average distance scale. So, if this were two helium atoms, epsilon is really small. And as we'll see, delta sigma is really big. But for water, for instance, epsilon is very big and sigma is very small. Waters like to be close, they're really strongly bound. Heliums like to be close, don't like to be close, bless you, and therefore like to be far away. So what does this look like on a plot? So I'm going to plot as a function of d, the potential.
Oh,
What's that?
the screen.
Oh, sorry, that's my knee again. There's some buttons down here that my knee hits and shuts it off. And so I want to plot this function on this plot. All right, so let's think about the limits of this function. As our d goes to 0 and d goes to infinity, what are the limits? All right, so if d is really large, this is a small number. This is a small number. So this whole thing is a small number. This is basically 0. All right, so at infinity, v is 0. At small d, this is a big number, this is a big number. In fact, it goes to infinity. Well, so as d goes to 0, this function goes to infinity.
It's half of infinity.
What's that?
That's it.
What's that?
Because it's one infinity minus another infinity.
Oh, well, you have to do 6. You have to do L'Hopital's rule 6 times to calculate the limit of. But yes, it goes to infinity. It's very easy to see that it goes to infinity. Yeah. And it goes to infinity because infinity to 12 goes faster to infinity than infinity to 6.
Yes.
So it wins.
That's why I was saying half infinity, but like.
Yeah. Yeah, you get the idea. And it's probably not too hard to see, but this is going to cross 0. And you just do the algebra, you'll find that there's a d where this is equal to 0. And so you'll, by the intermediate value theorem, it has to go negative. So what this function does is, so at small distances, the energy is very high. And then it crosses 0. It reaches a minimum. It has to, because it eventually goes back to 0, has to start rising again. And then it slowly approaches 0 as we go towards infinity. Right? You'll see that there is a position, which I'll call d star, that where the energy is minimum. That's the attractive minimum. Our potential, let me just remind you, when we talk about potential energy, positive potential is repulsive and negative potential is attractive. See? And that turns out, once you do the math, this is 6 root of 2 divided by times sigma, right? So sigma tells you something about where kind of the optimal position is between the two atoms. And the depth of this, how attractive the minimum is, this value right here, is minus epsilon. Right, so just like I said, right? Epsilon tells you how strong the attraction is, and sigma tells you where kind of the Goldilocks spot is between the two molecules. Okay. Now what I need to do is include, this is the potential energy of the interaction, but now I have to add heat to the system. So what is the energy? Let's say we have this, let's go ahead and do that. So let's just say I have 2 balls. And just to be careful, I'm going to say I have 2 of the same, right? Because Angie's right. It's a little tricky when I have 2 different ones. We have to consider like pairs and unlike pairs, and I just screwed it up as I said that. Right, and let's just set this to be, right, let's just freeze our atoms in place so that on average distance is these gone. Right, so we've got these 2 molecules locked into a place where they like to be. Optimally equilibrated. And then what I'm going to do is I'm going to set T equals 0 Kelvin. No heat. What's the total energy of the system? Bless you. The total energy of the system U is the potential energy plus TDS. Bless you. Or sorry, let me just say. Yeah, U is TD. Yeah, that's right, TDS. Entropy. Right, and at 0 Kelvin, this is 0. Okay? Because there's no entropy, 0 Kelvin. So the total energy is the potential at that. Right, so at 0 Kelvin, the energy of my system is right here, at the bottom of the well. Okay, so that's the energy. So when I bring in, so now imagine I have these 2 molecules at this position in energy. How much energy do I have to put into the system to break that attraction? Well, in order to separate the 2 atoms to infinity, I have to add in epsilon amount of energy, right? Because the attraction is epsilon. And so in order to break it, I have to put in epsilon energy to bring the potential to 0. And then the molecules are unbound. So this limit at V equals 0 is unbound. Right? We kind of have, if you think about it as if you have a ball down here, in order to get the ball out of the hill, you got to roll it up the hill. Right? And that's going to require this much energy to roll it up the hill. So now what happens as I start to heat the system up? So I mean, just before I say that, right? So that would mean here that the energy required at 0 Kelvin to break that would be epsilon. Now let's heat the system up. Well, let's just heat it up to, let's put it at liquid nitrogen temperatures. 77 Kelvin, that's liquid nitrogen. Now U is equal to V plus TDS, but TDS is non-zero now. You guys calculated for an ideal gas how much heat energy a system adds per unit temperature at constant T. At constant T, TDS is equal to 1/2 RT. Remember, you guys calculated in problem 1 or homework 1 that the average energy of an ideal gas is 3/2 RT. That was the answer to 1.3 or 1.4. That big question with Q, and it's calculated log of Q and stuff. The answer you got for the average energy is 3/2 RT. The reason why it's 3/2 RT is because an atom can move X, Y, and Z.
Wait,
There's three
that
different.
is-
Hold on a second. Hold on a second. An ideal gas can move in 3 dimensions. It can move X, it can move Y, it can move Z. It can move all of them individually, right? Because it can step X, it can then step Y, and then step Z. And so each motion is independent, if you will. And so the total energy of motion in 3 dimensions is 3/2 RT. This is a 1-dimensional potential. So the amount of heat that is provided to this motion along this axis D is 1/3 of what you would get in 3 dimensions. So that has to be 1/2. So that's a interesting, but it doesn't matter. We could write 3/2 RT if we want. We'd be off by a factor of 3. Who cares? It's a small number. And in general, we can actually say this is the thermal energy contribution to any single motion. Right, it's 1/2 RT. That's why RT is such a cool number. Right, it tells you exactly how much energy you put into something when you heat it up. If this were a motion that had 2 dimensions, like we had an angle and an R, right, then we would have RT heat, because there would be 1/2 RT in the stretching and another 1/2 RT in the angle. Or if we're in 3 dimensions, then it would be 3/2 RT. Or if we have 4 different modes, we could be 5/2, so we'd be 2 RT or 5/2 RT. Each motion brings to the table 1/2 RT. Right. So now what happens is now the energy of our molecules is now being bumped up higher by a unit of 1/2 RT as we crank up the temperature. Right. So let's say now at 77 Kelvin. Right, we add that much energy, now we're here. How much energy do we need to roll the ball out? Well, we don't need to roll it as far, right? We just need to roll it here. Crank the temperature up even higher. Right, maybe we're at 300 Kelvin. Let's say this is T equals 200 Kelvin. And then eventually, maybe we get it so hot, the amount of temperature is above the barrier. Maybe we're so hot that the amount of thermal energy we have is higher than the attraction. So let me ask you this question. Would we, if our energy is up here, where every molecule in your system has enough energy to roll out of this minimum, would we expect to see much contributions from the interactions between them? Anyone want to say yes or no? You're shaking your head. Yeah, no. Why?
Because the energy of the potential energy is basically it's so small that it's what's the word?
Negligible.
Negligible.
Exactly. So the idea is that TDS gets so large that V becomes negligible. And so once TDS is larger than the potential energy, we can just disregard the potential energy. The interaction doesn't matter anymore. So when we go back to that slide, page 2, and we look at the deviations, methane at 200 Kelvin, the average thermal energy is below that dissociation limit. So if the molecules are reasonably close together, they find each other, there's a high probability they'll stick together. So at 200 Kelvin, you're going to have, well, either you're going to have sticky molecules that are attractive, or you've crammed them in so far together that the exchange repulsion kicks in and they repel. But either of those forces are dominant because your thermal energy is very small. But now as I kick the thermal energy up, the average energy of my system now is above that potential. V is small compared to TDS. And so therefore the system just deviates as if it were an ideal gas. It just has kinetic energy, just heat, no potential. Of course, there is still some potential, right? But it's starting to fade away because in some sense V is getting progressively smaller than the heat. But you do notice that no matter what I do, even at high temperature, if the pressure gets really large, it still repels. And of course, the reason why that is, if we go back to our picture on the last page, over here, the molecules are completely free. But if you jam them close together enough, you're going to hit this repulsive wall. So at low pressure, the average distance is maybe out here. Right? The molecule distance is like right here. They're pretty far apart. They don't see each other. But at high pressure, you brought the density in so great, the molecule average distance between the molecules is really, really small now. And so at high pressure, it's over here. And so at high pressure, you're going to start pushing against that repulsive wall, and that's going to cause the molecules to blow up, right? And not to blow up, but to spread out, positively deviate in pressure, and hit the walls hard. So this is where the pressure dependence comes in. The energy, the heat dependence tells you where you are, how important the potential energy is. And then the pressure dependence tells you on average where your distances are. So at high pressure, you're at the repulsive limit no matter what. But the low pressure limit effectively looks like an unbound ideal gas. Okay. So this is a complete, very, very simple, complete picture of non-ideality. What we'll do next class on Tuesday is put this all together and come up with a new improvement to Pivner that takes in all of this information, and we'll see that we improve everything significantly. And then we'll think about the consequences. And that will lead us into phase transitions. So we're almost out of gases, guys. Very soon. And then we'll move on to liquids. Have a nice weekend.
Are we gonna do boxes of liquid probably
No.
instead?
No, we're going to stop. Eventually, we're going to move to constant pressure. And then we don't even have to worry about volume and stuff. Yeah, I'll introduce constant volume and constant pressure systems next week. And that'll be where we do most of our chemistry.
Have a good one.
Yeah, you too.
That's good. Is okay. So, a lot of your work would be getting access in.